This is the first video for Chapter 5, and in this one I just want to give you a little bit of an overview of random variables and discrete probability distributions, so that when you watch the other videos with the examples in them, you'll have more of an idea of what they're talking about. So in this chapter, we're taking the methods of descriptive statistics that we talked about in chapters 2 and 3, and also the probability ideas that we talked about in chapter 4. We're combining those two and coming up with probability distributions. So a probability distribution describes what will probably happen instead of what actually will happen or what did happen. And probability distributions are usually given in the form of a table, but they can also be represented as a graph or by a formula. Here's a little pictorial example of what we're talking about. If we have a simple procedure like rolling a die, we talked about doing this as an experiment and getting the frequencies. So in other words, collecting sample data, constructing a frequency distribution for the different outcomes of the die. We also talked in chapter 4 about finding the probability for each possible outcome, the theoretical probability. In this case, the probability for each outcome is 1/6. So now we're going to take those two things and combine them, and instead of a frequency distribution, we're going to have a probability distribution. Some key concepts that you need to know for this chapter. The first one is the concept of a random variable and how it relates to a probability distribution. Then we have two types of random variables, discrete and continuous, so you need to be able to distinguish between the two. Then we're going to look at formulas and actually more at procedures for finding mean, variance, and standard deviation for a probability distribution. And finally, we need to think a little bit about whether the outcomes in our probability distribution are likely to occur by chance or whether they are unusual in a statistical sense, in that they're not likely to occur by chance. So first of all, a random variable, we usually represent this by an x. This is one that has a single numerical value determined by chance for each different outcome of a procedure. And a probability distribution is just a table or a graph that gives the probability for each possible value of the random variable. So here's an example. In a carnival game, players are given 4 darts to throw at a wall of balloons. The possible outcomes for this game are that a player might pop 4 balloons, 3, 2, 1, or no balloons. So we can think of each one of these outcomes as being a possible value of a random variable x. And if we know, or if we can make an educated guess about the probability for each outcome, then we can create a probability distribution. So here's what a probability distribution for this game might look like. If we have some sample data that tells us that the probability of a player popping no balloons is about 0.13, popping 1 balloon is 0.34, and so on, then we're basically just writing down the outcomes and the probabilities for each one. Now, the difference between discrete and continuous random variables. This is kind of a tough one, but in chapter 5 we're going to be talking only about discrete random variables. These are the type where the outcomes are something that you can actually count. For example, how many balloons got popped. You can count something like that. It's possible to have a discrete random variable where there could be infinitely many values, but they're always going to be ones that could be actually counted. A continuous random variable usually comes from something that's measured, something like heights, weights, volumes, anything like that, where the actual value could be anything in a range of values. So there are no gaps or interruptions in the values. So I've got a couple of examples of variables that could be discrete or continuous. First is the number of oil spills off the Alaskan coast. So think about this, and is this something that could be counted? Well, the answer is yes. There could be no oil spills, there could be 1, there could be 10, so it would be something that you could count. That means that it's a discrete variable. Next example, the heights of a sample of LCCC students. Well, again, is this something that could be counted, or is this something that would be measured? The answer in this case is that the heights would be measured. They could be anything in a pretty large range of lengths. That would mean that this would be a continuous random variable. Just one example of a graph that shows us a probability distribution. This can be called lots of different things. In this slide, this is called a probability histogram. Notice that it's very much like a relative frequency histogram because the values on the vertical axis over here are in decimal form instead of percentage form, but they are relative frequencies. The values along the horizontal axis are the possible outcomes. They're the possible values of our random variable. There are two requirements for a probability distribution. The first one is that if you add up all the probabilities in the distribution, they have to add up to 1. The second one is that each of the probabilities individually has to be somewhere between 0 and 1. So in other words, they can't be negative and they can't be larger than 1. So here's an example. We have a table here with values for x and probabilities, and we want to know if this is a valid probability distribution. Well, we can look at each probability individually and see that each one of these is between 0 and 1. There are no negative values and there are no values that are larger than 1. So that requirement is satisfied. The next step would be to add up all the probabilities in that column and see if they add up to 1. Well, if we do this, if we add all those values up, we actually end up with 1.168. That means that this is not a valid probability distribution. Okay, some other things that we want to know if we have a probability distribution are the mean, the variance, and the standard deviation. I put these formulas on here just so that I could say that you had seen them, but honestly using the formulas this way is the hard way to do this. There are a couple of much easier ways to find these values. So here's an example of one way to find the mean of a probability distribution. So we have our probability distribution here, and what we're going to do is just add another column to this table. Once we get our third column, we're going to take each value of x, multiply it by its probability, and put that result in our third column. Once we get all those results, then we add them up, and that gives us our mean. It's going to look like this. For each one of these, we're multiplying the x by the p of x. That gives us these 5 values. We add all those up, and we get 1.62. That's our mean. To me, that's a lot easier than trying to use that formula on the previous slide. There is another way to do this if you have a TI calculator, which is really quick and easy. If you have one of these calculators, there's another video in the Chapter 5 folder about it. I would highly recommend that you watch that because it not only lets you find the mean, but it also lets you find the standard deviation. When we're finding values for mean, standard deviation, and variance with probability distributions, just like we did in previous chapters, we're going to carry our results to one more decimal place than the number of decimal places used for our original values of our variable. So as in the previous example where our values were whole numbers, want to carry it to one decimal place. One more thing about probability distributions and random variables, and that is in a lot of cases we want to find the expected value of our random variable. This is like the long run average of what our random variable is going to be, so what our outcomes are going to be. This doesn't mean in any one case that our random variable is going to have that value, but if we repeat the procedure or the experiment many times in a row, say 1,000 times or 10,000 times, then the expected value is the average value that we would expect to get. And notice down here, the expected value is exactly the same as the mean for a probability distribution. Notice it has the same formula. We would find it in exactly the same way as we just found the mean for that previous probability distribution.